everyone. Ever wondered how your phone sorts photos by date? How search engine finds what you're looking for in seconds? Or how online stores recommended products you might like? The secrets behind all these magic tricks lies into two core ideas of computer science: data structures and algorithm, or DSA for short. Today, we'll break this down so anyone can understand them with the real world example, a quick technical peek, and why they matter so much for the tech we use every day.
Animated slides defining each terms, plus simple diagrams showing the relationships. Let's start with the basics. First, what's a data structure? Think of it as a container for organizing and storing data. Just like a bookshelf, organize books by genre, author, and size. So you can find out what you need fast. And data structure arrange information in a specific way to make it easy to access, update, and manage. Common examples include arrays, linked lists, and stack and trees. Next, what's an algorithm? This is a step-by-step set of instructions to solve a specific problem or complete a task. It's like a recipe for baking a cake. Follow the exact step in order and you'll get a consistent result. For example, an algorithm could be the steps to sort a list of numbers from smallest to largest, or find a specific word in a dictionary. So how do they relate? Data structures provide the where for the store data, while algorithms provide the how to work with it. You would use it recipe algorithm to make cake without a mixing bowl or pan. Data structure, they work hand in hand to make computing efficient.
Real-life analogy. A real-life analogy in data structures means explaining how data is organized in a computer by comparing it to things we use or see every day, like lines, stocks, or folders, so it's easier to understand. Or short animation or real-life footage of a cafeteria line or library shelf. Let's make this concrete with an analogy for a stock. A popular data structure where items are added and removed from the top only. Lost in first act. For example, imagine a cafeteria tray stock. When stock or stock trays, they place each new one on the top of the pile. When you grab a tray, you take the top one. You wouldn't reach under the pile to pull out a tray from the bottom. That's exactly how stock works. The last item added is the first one used. Another example, your web browser back button. Every time you visit a new page, it gets added to the top of a stock. When you hit back, you go back to the page most recently added, the top of the stack. This setup keeps things simple because you only deal with the top item. In the cafeteria, no one wastes time rearranging trays. You just take the top one. In your browser, pressing back moves you step by step to the most recent page, not a random one. This kind of order makes everyday tasks faster, easier, and less confusing.
Hello, I'm Lizelle Abaracoso. My topic for today is technical examples. When we say technical examples, is cover specific hands-on abilities like programming, Python and Java. Data analysis is SQL and Tableau, and digital design is user experience and user interface, and Photoshop. Cloud computing is AWS and Azure, and technical writing is manuals and API docs. Now let's take a quick look at how we might describe a stack's behavior with pseudocode, a plain language way to show logic, no coding experience needed. We'll outline three basic actions. Adding an item is push, removing item is pop, and checking if the stack is empty. When we say stack, a stack works like a pile of plates. You can only use the top item. And the rule of stack is LIFO. LIFO means last in, first out. Push is an add item, like take a new item, place it on top of the stack, and stack size increases. And the pop is an remove item, like look at the top item and remove it, and stack size decreases. The purpose is known if the stack has items. If no items, stack is empty. If items exist, stack is no empty. See how simple does it? The pseudocode clearly lays out what each action does, no confusing syntax required. Thank you.
The next is significant. So why does DSE matter for software development? We have four. First is efficiency. Good DSE choices make program fast and useless memory. For example, a search engine using the right algorithm can scan might take hours. Second is scalability. It is apps grow like from 10 to 10 million users. Data structure algorithm ensure the skill work well. So scalability, it is a social media platform need to organize users' data to support load quickly for everyone. Third is problem solving. Data structure algorithm teach development how to think logically about complex problems. So it's the foundation for building everything from video games to medical software. Fourth, last is reusability. Core data structure and algorithm are used across almost all software learning. You can build or improve countless tools. So example this feature. Without DSE, the tech we really on very day would be slow, clunky, and unable to keep up without our needs. So data structure organized data like containers, algorithm are step-by-step introduction to work with that data. They are easy to understand with real-world example. Data structure organized data like containers, algorithm are step-by-step instructions to work with that data. They are easy to understand with real-world examples, and they are the backbone of modern. So that's all. Thank you for watching.